Let's see if I can move the webcam. Nope, it's not going to reach. Sorry, you're just going to have to look at the side of me. Okay, so we are checking over the 3.1 homework. 20 and 21 asked you to solve the equation graphically, right? Use the calculator to graph the function. And to find this point here, this is what we practiced a couple units ago, right? Finding the zero. So you should have been able to get 0.844, rounding to 3 decimal places. This one also said to solve the equation graphically by finding intersection. So essentially, all you need to do is graph the left side in y1 and the right side in y2 and find where they intersect each other. When you graph it, you're going to get a picture that looks something like this. And they intersect when x is 1 and when x is -6. And it said confirm your answer algebraically, which I did. And this is something, again, we talked about before, where you're going to set up two equations, right? 2x plus 5 can either equal 7 or it can equal -7. Do we do okay with those? Okay. How about 22? Not sure about that one? It's kind of confusing, right? So here's what we do. Your two inequalities, you're going to have x minus 3 is less than 2. But your other inequality is x minus 3 is greater than -2. So your -1 also changes the direction of the sign. Okay, so that means x is less than 5 and x is greater than 1. Write the solution in interval notation and draw its number line graph. So this means that x can be anything between 1 and 5, but not including 1 or 5, right? Because it's less than 5 and greater than 1. So if I draw this on a number line, okay, here's 0, 1, 2, 3, 4, 5. I would put open circles at 1 and 5. And then x can be all the numbers between 1 and 5. How'd we do? Nice. Dylan?
I had the right idea.
Okay. How'd you guys do this one? There's lots of ways you could go about it. I'll show you the way that I would do it. Okay? I'm actually going to solve the equation x cubed minus x equals 0. And to do that, I can take an x out. I can just solve this algebraically by factoring. That can be factored into x plus 1 times x minus 1. And so I get x equals 0, x equals -1, and x equals 1. Okay? Now, how does that help me? Well, I also know what this looks like if I graph it, because I know what a cubic function looks like. And I now know that it hits the x-axis at 0, -1, and 1, because that's where it equals 0. So it would have to look like this. And what does the question ask for? It asks for where this is greater than 0. So now we can see visually where are we above 0. So essentially, I'm looking at all the intervals that are above the x-axis. where I get a positive result. So this would be any number between -1 and 0, and any number from 1 to infinity. And I can include -1, 0, and 1 because the inequality is greater than or equal to 0. So essentially, anytime you have an inequality like this one as well, you're just going to want to find what values make it equal 0 first, and then you can determine what intervals are going to be greater than or less than 0. Right? Because what do I know about 6x squared minus 5x minus 4? I know that that's a parabola, right? And I can, if I know where it equals 0, I can then figure out based on what I know about parabolas where it's going to be greater than 0. I don't know. Is this factorable? Did anybody try to? You didn't try to factor it? Did you do the quadratic formula? Oh, you graphed it. Nice. Oh, it says graphically. Nice. Okay. So yeah, let's just punch it into the calculator. Six x squared minus 5x minus 4. Graph. Okay. So I'm going to find where we hit 0, which is negative 0.5. And 4/3 essentially, right? 1.3 repeating. All right, so we have -1/2 and 4/3. So again, I know that I'm greater than 0 on the two ends. So this will be -infinity to -1/2, and then 4/3 to infinity. Or if you wrote 1.3 repeating, that's fine too. All right, on to lesson 2. Yeehaw. So, exponential modeling. This should hopefully be a pretty quick lesson here. Essentially, what's going to happen is we are going to have some sort of scenario, and we have to be able to write an exponential function based on the scenario. So, all exponential functions are of this general form: a times b to the x. To figure out A is super easy to figure out. A is just your initial value. Whatever you are starting with, that is what A will be. To figure out B is going to be 1 plus R if it's growth. And decay, it's going to be 1 minus R, where R is the percent of change as a decimal. Okay, so for example, if I have 5% growth, B is 1.05. I'm doing 1 plus 5%, right? 5% is 0.05. If I have 5% decay, B would be 0.95. 1 minus 5%, 0.05. So example 1, it says, tell whether the population model is an exponential growth or decay function. Find the constant of percentage rate of growth or decay. So we have this equation that models the population of San Jose. And this is a number that is bigger than 1, which tells me that this is exponential growth. Okay. So 0.0136 really means 1.36%, and this is growth. It doesn't mean 0.0136%, it means 1.36%. Okay, Detroit population. B is less than 1, which means that this is decay, right? So I'm going to do 1 minus 0.9858 to figure out what that difference is. Okay, so 0.0142 means 1.42% decay. Okay. It's example 2 says determine the exponential function with initial value 12. So right away, that's going to be A. Increasing, that tells me it's exponential growth at a rate of 8% per year. So if I'm increasing at a rate of 8%, that means B is 1.08. So the function would be y equals 12 times 1.08. We'll do t because we're talking about time. But if you wanted to use x, you could, right? The letter itself doesn't matter that much. Okay, let's try example 3. Example 3 says, suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Now this one is a little different because it doesn't give us a percent change. But the fact that it doubles every hour tells me that B is 2. Write a function to model the population growth and determine when the number of bacteria will be 350,000. So I'm starting with 100 bacteria. So I'll say B for bacteria equals 100 times 2 to the T. We're good with the equation? Now let's think about if this makes sense, right? If T is 0, 2 to the 0 is 1. 100 times 1 is 100, right? Which is good. If T is 1, 2 to the 1 is 2. 100 times 2 is 200. If T is 2, 2 squared is 4. 4 times 100 is 400. So it's doing what we want it to do, right? We go 100, 200, 400, and so on. Now, I don't know about you, but I don't want to sit here trying to just punch in numbers until we get to 350,000. Okay? So what I'm going to do is I'm going to use my calculator. And I'm going to type this in. And I'm also going to type in 350,000. And I can find, I'm going to get this graph that goes like this. And eventually, it will hit 350,000, and I can find that intersection. Now, I'm going to have to adjust my window. Because if I just have y max of 10, I'm not going to see anything. So I'm going to go 500,000 and just kind of see what happens here. Okay, so what this graph tells me is that it's going to intersect much past 10 hours. So I need to adjust my window. We'll try 20. There it goes. Second trace, intersect, first curve, second curve, guess. Okay, so x equals 11.773. So we can solve this graphically. And we've talked about this before, but solving graphically is a strategy you can use for any scenario. If you have access to a calculator, it will work for any type of equation. Okay. Dylan, you took AP Chem, right?
Yeah.
Did you ever talk about half-life?
Yep.
What is half-life?
Half-life is the time it takes for a thing to reduce by half.
Or decay.
Yeah, decay by half.
Right? So there are certain substances or elements that are radioactive. They are not stable. And over time, they decay. And to measure the rate at which something decays, we use something called half-life. And the half-life tells us how long is it going to be until I only have half of what I started with. So if something has a short half-life, that means it's decaying rapidly. If something has a long half-life, that means it's decaying slowly, right? So this says, suppose the half-life of a certain radioactive substance is 20 days and there are 5 grams present initially. Find the time where there will be 1 gram of the substance remaining. Okay, now, anytime we talk about half-life, that means B is 1/2 or 0.5. Because I'm always going to have half of what I had before. And I know that A is 5 because that's what I started with. Now, where does this 20 days come into play? Well, let me show you. Let's see. I'll do G for grams. And my exponent is going to be T divided by 20. Now, let's talk about why. If T is 5, let's say, 5 days, it hasn't fully cut in half yet. It's not until when T is 20. Imagine there's a 20 here, right? 20 over 20 is 1. And now I will have reached 1 full half-life. And it won't cut in half again until T is 40, right? 40 divided by 20 would be 2. Now I've done 2 full half-lives. So whatever the length of your half-life is, you're going to have it in the exponent there dividing by it. Find the time when there will be 1 gram of the substance remaining. Well, I'm going to go to my handy dandy calculator and graph it again. I know that I'm going to be here at 5, and I want to figure out where do I hit 1 gram exactly. Okay. 5 times 0.5 to the x over 20. And I'm just going to put a 1 there. And again, I'm definitely going to want to change my window. Back to negative 10 to 10 should be just fine. And I definitely should have extended my window because when time is 20, I've only cut it in half twice. Although I'm getting close, or once. I've only cut it in half once. Let's do 60. All right, looks like there's an intersection somewhere in there. Boom, boom, boom. Let the calculator do all the work. So 46.439. Now, that is it for lesson 2, but I actually want to go back to lesson 1 and talk about interest. Now that we've talked about E and exponential modeling. So these are just formulas here. After T years, the balance A in an account with principal P, principal is like how much you initially put in the account, okay? And annual interest rate R in decimal form is given by the following formula. So for N compounding per year, right? So N is how many times we're calculating interest. And then this is continuous compounding. And it makes sense that we have E in there, right? Because E is all about continuous growth. It's the rate of continuous growth. So a total of $12,000, that's going to be P, that's our principal amount, is invested annually at an interest rate of 9%. So R is going to be 0.09. Find the balance after 5 years. That means T is 5. If it is compounded quarterly, monthly, or continuously. So for A, quarterly means that I'm compounding interest 4 times. And basically, this is just, can you plug all the right stuff into the calculator or into the formula? So my amount is going to be 12,000 times, and I'm just going to plug the numbers in. 1 plus 0.09 divided by 4 to the 4 times 5. Oh. To the 20th. So 18,726 and $11 or 11 cents. Okay, if I compound my interest monthly, that means N is 12. So I'm just going to grab that. And I'm going to change that to 12. And my exponent's going to turn into 60, right? 12 times 5. Nice, more money. Now, if I compound continuously, I'm going to use this formula, right? So I'm going to have A equals 12,000 times E to the 0.09 times 5. 12,000 times e to the 0.09 times 5. 18,819.75. So that would be the best that I could do with my 9% interest. It's compounding continuously. All right, so that is it for this lesson. The 3.2 homework is on the next 2 pages there. So a lot of these are, very similar to the examples we did. So you got this page and then this next page. So you have some review. You got some trig problems in there. And the numbering's all wacky, but I think you can figure it out. Thanks for joining if you're watching on the video. See you soon.